Okay, welcome to 3.5 regression number 2. Some key concepts we're going to hit in this lecture. Cleaning up or advancing our basic understanding of regression from the previous lecture. Prediction error, so understanding that when we're making predictions with the regression line that we're not always accurate. Talking about the sum total of those prediction errors with a new statistic, the standard error with the predictor, that's SY prime. And then a little more on the coefficient of determination R squared, which can be understood as variance accounted for or variance explained. And key relationship here, as R increases, prediction error decreases, that is SY prime, and variance explained R squared increases. So just to give you an overview of where we're going. So let's talk about prediction error. Prediction error occurs anytime you do regression because there's going to be gaps between the regression line and the scores. So this gap between the regression line, the predicted score, and 10 here is error, and each of these gaps between the actual scores and the regression line is error. So error has the simple formula y minus y prime. So in this case, let's assume here that it's crossing at 32. Conceptually, we have error then being equal to y, which has a value of 10 minus the 32, so it would be negative 22. In other words, this dot is falling 22 points below the regression line. So we're overestimating for this person. Overestimating for that person. And then for some other people, we're underestimating. So key rule here, as the variability decreases, your prediction accuracy what? In other words, as these dots fall closer to the regression line, as you get a stronger correlation, you're going to see your prediction accuracy increase. So note, you can also call these gaps between the regression line and the actual scores residuals. The way to think about that is this is the residual variability that's left over after you've applied the regression line. Okay, so what decreases error? First off, let's just compare these two. Between A and B, which relationship has a larger R? I think you'd say B, right? B has a stronger relationship between X and Y. So which has scores that are closer to the regression line? I think if you look here, you'd see that as the correlation gets stronger, the scores are falling closer to the regression line, which means what? The residuals are smaller down here than in outcome A. So, and notice the scaling is different here. Here you're seeing errors around 4. Down here our errors are closer to being around 1. So a lot less error down here. So what decreases error? The strength of the correlation. As the correlation gets stronger, you're going to have less error. Okay, so the second thing we're learning about here is the prediction error measure, SY prime, and this gives you the overall amount of prediction error. We just looked at a slide where I was talking about specific amounts of error for given scores, but here we're talking about overall what we'd call the standard error, the residual, standard error, the estimate, or standard error, the predictor, and that's calculated or represented by SY prime. So here we have two relationships, or two outcomes for the relationship between number of classes and stress level. Over here, there's very little correlation. You can just say no correlation. Over here, there's a strong relationship. So how does the error look different? If you have the error for a correlation here versus here, you're going to have a lot less error for the stronger relationship. So the variability here, we'd summarize SY prime as about 20, meaning that a band of +1 and -1 SY prime around the regression line captures that 68% of the variability. So this is functioning very much like a standard deviation. It's showing you that around the regression line you have a lot of error. Whereas over here, when you have a strong correlation, there's very little error around the regression line. So instead of needing 20 units to capture 68%, just 5 units captures 68%. So key thing here is, as the relationship gets stronger, the standard error of the residual, the standard error of the predictor, gets smaller. Okay, and then coefficient of determination, r squared. All right, excuse me. Our third point, coefficient of determination, r squared. So what this is the proportion of variance, or the fluctuation in one variable that's explained by another variable. Another way of thinking about it is it's the ratio of explained variance to the total variance. And then finally, let me give you one third handle. It's the increase in accuracy when using the regression line to make predictions. So this is a way of shorthand of explaining how much more accurate we are when we use the regression line to make predictions. So it's going to range from 0 to 1, and you get it simply by taking the r value and squaring it. And then typically you express that as a percent. So if r squared works to 0.23, you'd express it as 23%. Okay, r squared, you need three different ways to try to understand this, three different examples. So what we have here is two different graphs of the same data points. On the right-hand side, we're making our predictions using the regression line. So the scores vary around the regression line. You can see they fall very close. Over here, we're making our predictions based on the mean of y, so the scores are all over the place. On the left here, we're not taking advantage of this nice linear relationship. The error that you see then is large. So the squares represent the squared variance of the error. So we'd add up all the red area here and all the blue area here to make the comparison. So this is the total prediction error without using the regression line, the red areas, the pink areas. And then over here we have the error that's still remaining even after we've used the regression line to make our predictions. So we've done a lot better, but there's still a little bit of error. So what r squared does is it compares the total amount of error variance that's left to the total amount of error variance and subtracts it from 1. That gives you r squared. So what happens? As the correlation gets stronger, the error decreases, the blue squares shrink, and r squared increases. And again, you can think about r squared as just the difference between the red area, subtract out the blue area, and then all that difference is what we'd explained with the regression equation. Okay, so here's another way of thinking about it. On the left-hand side, we have a situation where there's a really small r, virtually 0, and our measure of variability around the regression line, standard error of the residual, is 20, and over here it's 5. So we're accounting for a lot more variance here on the right-hand side. So if we square r here, it's virtually 0. We square r here, it's 0.89 something. So here we're accounting for about 90% of the variance with the regression line. Here only just a pittance, almost 0. So again, the difference is the difference between this red area and this blue area. That would be the variance accounted for. Okay, then one more shot at this, and these are all trying to get across the same thing, just what r squared means. So we start off with the mean of the relationship, the mean of y. So in this case 60, and you then look at an individual score, and then what we can say is this represents the total variance. In other words, this is how much error we have relative to the mean. So we would do this for each score and figure out how much the total variance is. With the regression line, you note that we do a lot better in predicting this score. So instead of having this much error, we only have this little error at the top that remains unexplained. We have all this error that we're explaining based on the regression line. So another way of saying that is these measures of error are going to be a lot smaller if we're comparing to the regression line versus comparing to the mean. Those are just various ways of saying that we're accounting more for more variance, and that's what the r squared ultimately tells you. So, and then bottom line, if we can account for more variance, if we can explain more of this variability of the scores, we make better predictions, and we make better predictions as the strength of the correlation increases. Okay, to find R squared and SY prime with SPSS, I'm going to point you to the same SPSS guide that is your guide for correlation and regression on SPSS in the front part of your course pack. The R squared here is in the top of the two tables that we look at. It's a coefficient of determination, in other words, the amount of variance explained in the predictor, and the SY prime is found here at the very end. It's labeled there the standard error of the estimate. And again, that's the overall amount of prediction error that you have when you're making predictions. And that's it. That concludes our second lecture on regression. Thank you.